All right, hi everyone. This is Miss Bung again. Today we are continuing with our lesson 12.3, which is all about trig functions of general angles. That is, angles that aren't by default necessarily attached to right triangles, although you might have a sense from what we covered last time that we are generally trying to draw right triangles using those angles. We talked about those reference angles last. Now we're going to be looking at using some known trig ratios. So there will be a little bit of memorization to a degree involved, but let me tell you what I mean by that. So today we're going to start with a little bit of a warm-up. We are looking at two specific right triangles here, and we want to determine the missing side lengths of these two triangles. Now we're going to strive to leave our answers in what we're going to call exact form, which means simplified fractions and potentially simplified square roots. So if you would like to follow along with this, I want you to maybe go ahead and pause so that you can actually sketch out these triangles. Okay, so I'm actually going to dive into this. Now let's maybe focus on our triangle here that's labeled with 45-degree angles, and as we can see, a right angle there in the corner. So we're given that the hypotenuse here is 1. Remember, that's our hypotenuse. If we're trying to solve for x, there's potentially a couple ways we could go about doing that. I'm going to use the Pythagorean theorem. I want to look at our a squared plus b squared equals c squared, but plug in the information specific to our triangle. So a and b, remember, those are just the legs of the triangle, of the right triangle. Those are both x. So we're actually looking at x squared plus x squared equals, well, not c squared, but in particular here, 1 squared. So x squared plus x squared, well, that's actually just 2x squared, and 1 squared is just 1. So again, if I'm solving for x, it looks like I'm going to need to, well, divide by 2 to have x squared is equal to 1/2. And then we'll take the square root of both sides. X is equal to the square root of 1/2. Okay, so let's think about simplifying this thing. When we're taking the square root of a fraction, that's the same thing as taking the square root of both the numerator and the denominator. But of course, I can't leave that square root in the denominator. It's one of my syntax rules here. So that means I need to get rid of that by multiplying both the top and the bottom by the square root of 2. So what that's going to be equal to then is, okay, the square root of 1 times the square root of 2, that's just still the square root of 2. I should have said square root of 1 is equal to 1. And that's over the square root of 2 squared, or just 2. So this means x is equal to the square root of 2 over 2. Both legs of my triangle here are equal to the square root of 2 over 2. Now that's how I could solve for x using the Pythagorean theorem. Perhaps I could also solve using trigonometry. So maybe I could say instead that if I'm considering this 45-degree angle as my angle of reference, I could say perhaps that the sine of 45 degrees is equal to, okay, the opposite, that's x, over the hypotenuse, that's just 1. So I'm actually saying that 1 times the sine of 45 is equal to x, or just sine of 45 is equal to x. Now on our new calculators, the TI, what is it, TI 84 plus CEs, if I plug in sine of 45, I don't get this exact form, square root of 2 over 2, but I want you to maybe practice comparing those values. So for example, I get, when I plug that in, 0.707106, blah, blah, blah. And if I actually plug in separately the square root of 2 divided by 2, I get the exact same answer, 0.707106, blah, blah, blah. And I can see that the further digits that I didn't bother writing down, they still match up. So this is going to be something that I actually start to commit to memory. We'll talk about that in a moment, but square root of 2 over 2 is going to be a value we see a lot when we're talking about our trigonometry values. So maybe let's move on to the next problem. We're solving for y and for z here. So I need to, let's see, I'm not sure I can use the Pythagorean theorem necessarily because I'll have two unknown variables, but I think I could use trig. I maybe want to look at, let's start with this 60-degree angle here. So this 30-degree angle, sorry about that. This 30-degree angle, if that's my angle of reference, then it looks like I could probably easily solve for either y or z. I'm going to start for y. So I can write that sine of 30 degrees is equal to y, that's my opposite, over 1. That's given as my, again, my hypotenuse here. So let's see, that's going to look like sine of 30 is equal to y. Again, maybe I don't right now have sine of 30 memorized. I think we will soon though. If I plug that into my calculator though, you're going to notice that we get 0.5. Now I'm going to write that as a fraction. 0.5 as a fraction is just 1/2. So we will see that across from our 30-degree angle here, we're going to have 1/2. Y is equal to 1/2. Now I could do the same thing. I could use trig to solve for z. I'm wondering though, what if I actually use the Pythagorean theorem? Why not? So again, we've got a squared plus b squared equals c squared, but that's actually in this case going to be 1/2 squared plus z squared, my other leg, is equal to 1 squared, or 1/4 plus z squared is equal to just 1. Okay, so if we subtract 1/4 from both sides, we get z squared is equal to, let's see, 1 minus 1/4 is really 4 over 4 minus 1/4, so 3/4. So if we take the square root of both sides, again, similar to as before, we take the square root of both the top and the bottom. And fortunately, this time we don't have to rationalize because the square root of 4 just simplifies down to 2. So the square root of 3 over 2 is my answer for z. So kind of the same as before, I could have used trig, right? I could have said perhaps the cosine of 30 degrees is equal to z over 1, which if we multiply both sides by 1 just means the cosine of 30 is equal to z. But same kind of idea as before, if I plug this into my calculator, cosine of 30, I get a long decimal. And in fact, my calculator isn't even necessarily showing me the full decimal, it just kind of cuts off at a specific place. I get like 0.0, or I guess 0.86602, blah, blah, blah. Let's check if that's actually the same thing as root 3 over 2. So square root of 3 divided by 2 comes out to be the exact same thing. 0.86602, blah, blah, blah. Same blah, blah, blahs. So this again, the square root of 3 over 2, this 1/2, and this square root of 2 over 2, these are values that I'm going to see over and over again. and ones that I'm going to want to try to start committing to memory. And we're going to sort of hash that here in just a second. So let's talk about our 45, 45, 90 right triangles. So named because we have a 45-degree angle, another 45-degree angle, and a 90-degree angle. So in these 45, 45, 90 triangles, we're going to see the same side lengths over and over and over again. Now, if we're sort of building into talking about something we'll call the unit circle later this unit, we're always going to make our hypotenuse of these triangles equal to just 1. So just like we looked at before, we on this page are trying to reestablish what is x equal to. What are our legs? And our legs are actually the same. They're both equal to x. I'm not necessarily going to repeat that work. I'm just going to sort of pull that over and say, well, this is actually the square root of 2 over 2, like we said. And we have the square root of 2 over 2 here. Let's use that now to determine what is the sine of 45 degrees, the cosine, and the tangent of 45 degrees. So if we're looking at the sine of 45, let's just pick one of our 45-degree angles. We don't need to talk about both of them, but they will have the same trig value since they're the same degree. So I picked one of mine to be my reference angle. So opposite, remember sine is the opposite over hypotenuse. That's the SO part of SOHCAHTOA. Remember, always write that out if you feel like it's helpful to you. So opposite here is square root of 2 over 2. That's over my hypotenuse, which is 1. Okay, well anything, even if it's a fraction, divided by 1 is just itself. So our fraction is the answer. That's square root of 2 over 2. Sine of 45 degrees is square root of 2 over 2. Let's look at cosine. So this is the part of SOHCAHTOA, adjacent over hypotenuse, and this comes out to be the exact same. We're still looking at the square root of 2 over 2, just this one this time. The adjacent side happens to have the same measure. So we're looking at the square root of 2 over 2 over that hypotenuse of 1. It's still going to simplify to the square root of 2 over 2. Okay, let's look at the tangent then. That is the TOA opposite over adjacent, or square root of 2 over 2 over square root of 2 over 2. I mean, I could think about simplifying this as we did rational expressions a chapter ago, but ultimately this is a number divided by itself, like 3 divided by 3. It just is a slightly more complicated looking number. That is always just going to be equal to 1. 3 divided by 3 is equal to 1, just like square root of 2 divided by 2 divided by square root of 2 divided by 2 is equal to 1. So these values, the sine of 45 degrees equals square root of 2 over 2, so does the cosine of 45 degrees, and the tangent of 45 equals 1. These are things we're going to want to start to remember. So make sure you pause if you need to get this written down very clearly in your notes, because this is something we're going to come back to frequently. We're going to move on though and talk about our other types of very special triangles, our 30, 60, 90 triangles. So these are again so named because we've got a 30-degree angle, a 60-degree angle, and a 90-degree angle. So we're going to identify the 3 main trig functions for each of these. So that means I'm also going to pull sort of from my warm-up what the measurements of the sides I've labeled y and z are. So y across from my 30-degree angle there is 1/2, and z across the triangle from that 60-degree angle is the square root of 3 over 2. Okay, let's maybe look at sine first. So the sine, let's look at sine. Let's look at 30 degrees first as our reference angle. And let's start with the sine of 30 degrees. So the sine of 30 degrees opposite over hypotenuse is 1/2 over 1, which simplifies as before just to 1/2. The cosine of 30 degrees adjacent over hypotenuse will be the square root of 3 over 2 over 1, or again just the square root of 3 over 2. Now the tangent, this one's maybe a little bit more complicated. The tangent is going to start with the opposite, that's 1/2. I'm going to do this work over here actually. 1/2 over the adjacent, square root of 3 over 2. Now this is kind of a complicated looking fraction. But I want to remind us that when we are dividing by a fraction like this, we could also just multiply by that reciprocal. So that means this could be rewritten as 1/2 times, well, the reciprocal of that denominator would be 2 over the square root of 3. So we'd be looking at, let's see, 2 over 2 root 3. I don't like that I have a square root there, so I need to rationalize, meaning we need to multiply by the square root of 3 over the square root of 3. To get 2 root 3 over 2 root 3 squared, or 2 just times regular old 3. Oh, but that simplifies. Maybe I could have simplified earlier, in fact. This simplifies all the way to the square root of 3 over 3. That's the tangent of 30 degrees. And again, exact form. You could confirm that on your calculator. Plug in tangent of 30, see what the decimal value is, and then plug in the square root of 3 over 3, compare those decimals. We'll get the same answers. So let's maybe look at the sine, cosine, and tangent of 60 degrees. So what happens when we pick the other angle as our angle of reference? So let's see, sine of 60. Now all of a sudden our opposite over our adjacent is square root of 3 over 2 over 1, which is the square root of 3 over 2. You might see where this is going. The cosine of 60 degrees is going to be 1/2 over 1, or just 1/2. Now what about that tangent of 60 degrees? That's going to come out to kind of a nice square root of 3. But let's maybe look at why. The tangent of 60 degrees, again, is the square root of 3 over 2. That's our opposite, all over 1/2. However, that's going to be the same as multiplying the square root of 3 over 2 by the reciprocal of 1/2, multiplying by 2 over 1. And that is going to just be equal to the square root of 3. We could maybe cross cancel our 2's out there, or we could get the result 2 root 3 over 2 and see that we've got a common factor of 2 that can cancel out. So the square root of 3 is the tangent of 60 degrees. Again, some valuable things to start committing to memory. A big reason is due to our unit circle. And this is something we are building up to, so we're sort of going to get more and more specific as we get closer to that. But a unit circle is made up actually of a bunch of these exact same triangles. So I want to just give you a little preview here. This is what a unit circle looks like. I know it looks a little scary perhaps at first, but it is actually a bunch of the same pattern over and over. So our unit circle, the first thing to know, is always going to have a radius of 1. So all of these lines have a length of 1 unit. That's why we call it the unit circle. Now we can also see that there are a series of 45, 45, 90, and 30, 60, 90 right triangles. It might help for now if I actually show the degree measures instead of the radian measures of all of these various points. So I just want to show that here, this first angle, the angle measure is kind of given here at this point as pi over 6. Well, pi over 6 is radians. That's going to be equal actually to 30 degrees. Hopefully you feel like if you put your mind to it, you could convert that. Now, if we said, what about this pi over 4, this angle here? That's actually going to be our 45 degrees. And you probably see what's coming here. Up here at pi over 3, that's in fact going to be 60 degrees. And our pi over 2, that is, of course, 90 degrees. I'm not really going to bother labeling the entire circle here. What I want us to maybe recognize here at first, though, is that we've got these triangles. Here's the 30, 60, 90. We know that this angle is 60. This, of course, is going to be our right angle. So this has to be a 30-degree angle. We can see another one of those here just kind of turned on its side. A 30-degree angle here, a right angle, and then our 60-degree angle. We also have a 45, 45, 90. So we've got our 90-degree angle and then our 45-degree angles. There are a bunch of those that we can end up drawing inside of this triangle that coordinate with these various points that we're interested in. So what I want us to know for now is that the coordinates of the given points on this unit circle are going to be determined by the cosine of whatever theta is for our x and the sine of whatever theta is for our y. So cosine of theta will be x and sine of theta will be y. And that's because all of these little triangles, again, the radius is 1, so all of these triangles have a hypotenuse of 1. If I'm talking about this 30-degree angle, well, I know across the triangle from that 30-degree angle, the measurement of this side is 1/2, and the measurement of this side, or the length of this side, I guess I could say, is √3/2. So my coordinates then of this point are going to be √3/2, comma 1/2. I go over √3/2, I go up 1/2. So those are the coordinates of that point. We'll kind of work on remembering that as we go forward. So we'll be able to label, let me just maybe draw that that's the coordinates of that particular point there. We'll be able to label all of these coordinates, again, using these special right triangles. So for example, here's our √2/2 and our √2/2. If I'm talking now about my 45, 45, 90 right triangle, which means the coordinates right here at this 45-degree angle are going to be √2/2, comma √2/2. So this becomes really handy for me to be able to kind of convert between recognizing the coordinates, so the coordinates of 30 degrees and the coordinates of 45 degrees correspond directly to the cosine and the sine of those angles. So again, something we'll work on gradually, committing to memory. Let's maybe look at why this is actually helpful. So this was all about helping us determine the exact values, or determine the trig values of particular angles, general angles. Let's do some examples. You'll see questions like this. Find the exact value, that's going to be, again, fractions and or square roots of some angle. So that's some angle, 135 degrees. I told you at the beginning of this chapter, you don't have to have things like this memorized, and that's true, but we're going to do some problem solving in order to figure this out. Notably, 135 degrees, that's actually 90 plus 45 degrees. That breaks down as 90 plus 45. So maybe I'll just start by sketching that angle out. So I've got my axes already drawn here. Let's draw my initial side and then my terminal side. So here's my little directional angle. This is 135 degrees. Notice it goes past 90 degrees. In fact, it goes 45 degrees past 90 degrees. So in order to determine let's see, what am I asked to find? The sine of 135 degrees. I want to figure out where is my reference angle. That reference angle is always formed directly with the terminal side and our x-axis. So my reference angle theta prime is here. What is my reference angle? My reference angle, in this case, how many degrees further do I have to go so that I have my terminal on the x-axis? I have to go 45 more degrees. So 135 plus 45 would be equal to 180. Of course, 180 representing the x-axis here. So my angle of reference, my reference angle, I guess I should say, is equal to 45 degrees. That means I can think about drawing out a little triangle just like we did before. I can pull down my my side here. Think about this as a side of my triangle, and think of my my terminal side as also a side of my triangle. Except this is a 45-degree angle. I know that if I just set the hypotenuse to equal 1, then the sides here are equal to the square root of 2 over 2 and the square root of 2 over 2. So therefore, the sine of this reference angle, the sine of 45 degrees, is equal again to the square root of 2 over 1, or just the square root of 2 over 2. This is the exact sine of 135 degrees. Again, because we're using our reference angle here, which is 45 degrees. The sine of 135 degrees is equal to the sine of 45 degrees. Let's look at another example, maybe this time using our radians. Maybe we're a little bit more uncomfortable still with using radians. Let's check that out. So we're given, let's see, the cotangent of 7 pi over 3. Okay, let's start by labeling my axes. Remember that our positive x-axis, that's always basically 0 degrees or 360 degrees. But if I'm talking about radians, that's still 0 radians or 2 pi radians. So a full rotation would be back at 2 pi radians. 90 degrees would usually go here, but if we're talking about radians, then that's going to be pi over 2. Okay, usually this would be 180 degrees, but in radians, that's pi. And again, usually this would be 270 but in degrees, but in radians, that is 3 pi over 2. Okay, so let's think. 7 pi over 3. 7 pi over 3. You know what? That's more than 2 pi, isn't it? Because 2 pi is equal to, in terms of 3, that would be equal to 6 pi over 3. So wow, we're going actually around our circle and further. So we're doing a full rotation plus some. In fact, this would be one full rotation plus a third. Let's see, plus pi over 3. I guess I should say it would be 2 rotations, or 2 pi. 2 pi, not 2 rotations. Let me make sure I can actually speak there. There we go. So we've got 2 pi. Maybe I'll in fact write that out. 2 pi plus a pi over 3. So we're starting here with our initial side and then looping around. We're like going a full circle and then some. We're going pi over 3 some, in fact. So let's make this my estimation of where my terminal side would be. And then my directional is going to show like we're looping around the axis a little bit more than once. So that's my angle 7 pi over 3. Okay, so again, same idea. We want to determine what is my reference angle. So my reference angle here, that's going to be pi over 3. Notice I went around a full circle, 2 pi, and then I had to keep going a pi over 3. This is actually also my reference angle, the angle formed by the terminal and my x-axis. So if we make our triangle again, we've got, and maybe I'll sketch this triangle just so it doesn't get too busy. I'll sketch it out here. We've got an angle of pi over 3. Might be helpful at this point to kind of convert that. How many degrees is pi over 3 to begin with? Well, let's think about that. Pi over 3 compared to a full circle, 2 pi, full rotation, is equal to how many degrees out of a full circle? 360. All right, I might cross multiply to get 360 pi divided by 3 is equal to 2 pi times my angle in degrees. Let's maybe go this way. So 360 divided by 3, well, that comes out kind of nicely. 360 divided by 3 is just 120, so I have 120 pi. That's equal to 2 pi times my angle. Let's divide by 2 pi to get 60. So actually this angle is 60 degrees. My angle of reference, or theta prime, is 60 degrees. So again, let's maybe say, well, that hypotenuse is going to be 1 across the triangle from my 60 degree angle. I'm going to have this square root of 3 over 2. And then sort of next to, or across, maybe from 30 degrees, I'll have 1/2. So the cotangent. All right, we got to remember what the cotangent is. Cotangent, the reciprocal of tangent, is adjacent over opposite, whereas tangent is just opposite over adjacent. So the cotangent of 7 pi over 3, which is the same thing as the cotangent of pi over 3, which is the same thing as the cotangent of 60 degrees, my goodness, that is going to be equal to 1/2 over the square root of 3 times 2. And if again we simplify this, we'll have 1/2 times the reciprocal, 2 over the square root of 3. Let's maybe cross cancel our 2's and see that that's 1 over the square root of 3. Womp womp, still not done. Square root of 3 over the square root of 3, I need to be multiplying. I guess I'm kind of writing things a little bit out of order, sorry. Is equal now to the square root of 3 over 3. Phew. Okay. So that is the answer to the cotangent of 7 pi over 3. So a little bit involved there. Now I'm going to skip our next example. I want to talk about maybe how we might work backwards. So I'm going to skip over finding the sine of 120 degrees. and talk about this kind of problem. If the sine of theta is equal to something, the square root of 3 over 2, and theta is in quadrant 2, we want to find theta, or excuse me, cosine of theta. So let's think about our quadrants for a moment. I know that my angle is going to end up, my terminal side I should say, is going to end up in quadrant 2. So it's going to be somewhere over here. And of course my initial side is here-ish. So in quadrant 2, remember this is quadrant 1, here's quadrant 2, 3 is down here, 4 is over here. What is positive and what is negative? Well, in 1, our x is positive and our y is positive. In 2, our x is actually negative and our y is positive. In quadrant 3, well, they're both negative. Our x is negative, our y is negative. And in quadrant 4, our y is negative, but our x is back to positive. So if the sine of some angle theta is equal to the square root of 3 over 2, let's think about what that means. Maybe I'll sketch my angle theta first. So of course, well, I've already got my angle theta, but I think I should say let's sketch our reference angle theta prime. Here's that reference angle. Let's draw our right triangle. The sine of this is square root of 3 over 2. Again, I'm going to say let's make that hypotenuse equal to 1, which means the opposite is going to have to be the square root of 3 over 2 in order for the sine of this angle to be equal to the square root of 3 over 2. If that's the case, I have the makings of a 30, 60, 90 right triangle right here. The missing dimension, this missing side length of my triangle, is going to have to be equal to 1/2. But notice I'm in quadrant 2 where the where the x values, the distance I'm going off to the x direction, has to be negative. So this dimension of my triangle is negative 1/2. That also directly corresponds for me to the cosine of my angle, because the cosine of my angle is the adjacent side over the hypotenuse, which is just 1. So the cosine of my angle, it doesn't matter what that angle is, I don't need to determine that, it's negative 1/2. Let's do just one more really quick one just like this. If I know the cosine of some angle is negative 1/2, and it's in quadrant 3, you might have thought we were doing the exact same problem. Nope, it's in quadrant 3. I want to find sine of theta. So let's just sketch that. We've got our initial side, and then we've got quadrant 3 down here. So somewhere down here. Doesn't have to be perfect by any means. This is my regular angle theta, which means where is my reference angle? It's here. Remember, it's always formed with my x-axis and the terminal side of the angle. So I am looking then at a triangle here. In fact, I maybe want to clean this up just a tad so that we can focus a little bit. We are looking at a right triangle where I know the cosine is negative 1/2. Well, that's convenient because, in fact, in quadrant 3, both the x and the y are negative. So the direction I'm going off into the x direction is supposed to be negative, and it is in fact negative 1/2. Remember, this is our angle theta prime, our reference angle. So the adjacent side along the x-axis there is what I'm given with cosine. Again, I'm going to make that hypotenuse just equal to 1. So what am I missing here? What's the missing dimension? What's the missing side length? Well, again, back to thinking about these 30, 60, 90 right triangles. What goes with 1/1/2? Root 3 over 2. And in particular, negative, because again, we're going into quadrant 3 where the y values, the direction I'm going in the y direction, is negative. So the sine of my angle theta is negative root 3 over 2 all over 1, or negative root 3 over 2. Okay, so you're going to have some practice with this. We'll talk more and more about that unit circle as we get closer to that lesson. But give yourself some time to let this information process. Come back to it as often as you may need, and I'll be available for questions as well. Okay, have a great day.